Who are you? What do you want?
He lost his fiancée a month ago. He wanted to see her just once more, so he tried with quantum principles. The quantum principle explains the ghost. Patent pending. JP application now 2026-99639. Quantum circuit anomalous transaction detection. You're on a soft co. Limited.
Who are you? What do you want?
The quantum principle explains the ghost. Chapter 1. The ghost is neither here nor gone. A hallway, late at night, at the corner where no one should be, a pale figure appeared. He blinked once, and no one was there. Was she there, or was she not? In the quantum world, the answer is neither. It is both. Picture a spinning coin. While it spins, it is neither heads nor tails. Heads and tails overlapping, trembling together. We call this superposition. The shape of her present and the shape of her gone. While no one watches, the two stay overlapped, trembling in the hallway. In code, it is a single line. Apply one H-gate to one qubit. That alone creates a state where 0 and 1 overlap, half and half. Measure that state 1,000 times. The result, roughly 500 times 0, roughly 500 times 1. The same answer never returns twice. Present and absent, appearing half and half. The very same behavior as the figure in that hallway. So why does she vanish the moment she is seen? In Chapter 2, we solve that mystery. The quantum principle explains the ghost. Chapter 2, vanishing the moment she is seen. He set a camera in the hallway. If she appeared again, this time, he would be certain. 2 in the morning, a pale shape rose at the corner. He held his breath and stared. In the next instant, the shape was gone. Unseen, she is that. Seen, she vanishes as if she cannot bear to be watched. In the quantum world, this is ordinary. Two overlapping shapes collapse the moment they are measured into just one. Press a spinning coin under your palm. The instant you press, it becomes heads or tails. Until you press, it is undecided. What decides is not the coin, it is the pressing hand. The act of measuring itself chooses a single answer. We confirm it in code. After the H-gate, we measure. In this one line, the overlap collapses to 1. Measure once, then measure the same qubit again. Now, across 1,000 shots, the same answer returns every time. See 0, and it stays 0 forever. The moment he aimed the camera, perhaps she was fixed at the absent side. So, why can she pass through walls? In Chapter 3, we solve that mystery. The quantum principle explains the ghost. Chapter 3, passing through the wall. At night, she stood in a locked room. No windows. He could only think she must have come through the wall. Throw a ball at a wall, and it bounces back. Without enough force to climb it, it never reaches the other side. So says our common sense. But a tiny particle is different. Most of the time it bounces back, but very rarely it appears on the far side. We call this tunneling. A particle is not a sharp point, but a blurred, spreading wave. The tail of that wave soaks a little into the wall and pokes out faintly on the other side. how much leaks through drops sharply as the wall grows thicker. A thin wall, sometimes passable. A thick wall, almost never, and yet, never quite zero. This is no fantasy. The sun keeps burning, and a USB drive erases data, both by tunneling. The scanning tunneling microscope measures this leak to see single atoms. In code, we set the wall's thinness as an angle, apply a small angle, and measure 1,000 times. The far side appeared about 20 times. Now have the angle. That means a thicker wall. The passes drop to about 5, a quarter as many, but not 0. Perhaps she could pass, not because it was possible, but because it was merely rare. So why was she seen in 2 places on the same night? In Chapter 4, we solve that mystery. The quantum principle explains the ghost. Chapter 4, seen in 2 places the same night. The record of that night, 2:40 a.m. He saw her in the first floor hallway. At almost the same moment, a neighbor saw her standing at a second floor window. The same moment, 2 places, the downstairs hall and the upstairs bedroom. Was she there as 2 people? The upstairs bedroom has 2 doors, one from the hall, one through the study. Which one she came through, no one saw. Sent tiny particles through a wall with 2 slits. Even firing one at a time on the far wall, stripes appear. Stripes can only form when both paths are taken at once. Block one slit, and the stripes vanish. On the floor that night, there were stripes. So we watch to see which door. The instant a camera is placed on a door, the stripes vanish. Seen, she takes only one path. We confirm it in code. Apply the H-gate twice and measure 1,000 times. The result, all 1,000 come out 0. The 2 paths line up into one answer. Now we measure once in the middle. That means we saw which path. The result, 0 about 500, 1 about 500. The stripes are gone, scattered again. She walked both paths at once. The moment she was watched, she was cut down to 1. The hallway behind you right now, no one is watching it. Chapter 5, the white mist in the photograph. The quantum principle explains the ghost. Chapter 5, the white mist in the photograph. He pressed the shutter toward the empty hallway, where no one should be. In the developed photo, a white mist had appeared. Is empty space truly empty? Here enters Heisenberg's uncertainty principle. Position and momentum cannot both be pinned down at once. So even cooled to absolute 0, minus 273.15 degrees, the trembling never stops. We call this 0-point motion. Perfect stillness does not exist in this world. The same happens in seemingly empty space. A particle and its partner are born in pairs and vanish at once. This trembling is the vacuum fluctuation. The particles are called virtual particles. No fiction. Bring 2 metal plates extremely close, and the trembling allowed between them is restricted, so a force pushes them from outside. The Casimir effect, predicted in 1948, measured in 1997. The same is thought to happen at a black hole's edge. Of a pair, one falls in, one escapes, Hawking radiation, but this, no one has yet observed. In code, we apply no gate at all. Just measure 1,000 times. On an ideal machine, all 1,000 are 0. But on a real quantum computer, one appears 10 to 30 times, though we did nothing. This is the noise left in the device. The white mist may be the trembling of empty space itself. Look at that photo once more. In the mist, are there not eyes? Chapter 6. In a distant house at the same time. The quantum principle explains the ghost. Chapter 6. In a distant house at the same time. The same night, 2:40 a.m., 300 kilometers away, at her family home, the same thing happened. The hallway clock stopped. The photo frame fell. The very same moment as his house. Apart, yet aligned, the quantum world has a close cousin of this. Its name, entanglement. Two particles, however far apart, measure one, and the other's answer is fixed. With gloves, it is simple. Take the right one out, and the left stays home. Before you open the box, the contents were already decided. But entanglement, this cannot explain. The measuring stick is Bell's inequality. If the contents were decided from the start, there is a limit to how much they can align, never to be crossed. Shown by Bell in 1964. Tested by Aspect in 1982, and in 2015, an experiment closing the loopholes. The 2022 Nobel Prize in Physics. That limit is 2, but entanglement aligns up to 2.828. The experiment crossed the limit, which means it was not decided from the start. Still, no signal can be sent. This is the no signaling theorem. What each house sees is just a record of zeros and ones scattered. Nothing can be conveyed to the other. We build it in code. H on the first, C not on the second. Now 2 entangled qubits exist. Measure 1,000 times. 0, 0 about 500. 1, 1 about 500, 0, 1, and 1, 0. Never once. Each house's record, alone, is just scatter. Only when the two records are compared do we find they always match. To compare, you need a phone call. It is no faster than light. What she caused in two houses at once may have been entanglement. And now, a phone is ringing from that house where no one should be. Chapter 7. Summoning the Ghost with Code. The quantum principle explains the ghost. The final chapter, 7. Summoning the Ghost with Code. Over 3 months he wrote a single program to find one target among a vast sea of candidates. Grover's search. Picture apples lined up in a cage. First, gently push down only the apple you want. Phase inversion. Then, reflect everything about the average. Now that one apple leaps high above the rest. Amplitude amplification. 1,024 candidates. Push down. Then lift up. Repeat this 25 times, and the chance of the target appearing passes 99.9%. He pressed the run key. She had picked, but the moment he reached out, her outline broke apart. The instant she touched the surrounding air and light, the overlap shattered. We call this to coherence. Then could he copy her and keep one at hand? He cannot. It is proven that a quantum state cannot be copied. The no-floating theorem, 1982. Sending her, that he can do quantum teleportation, but the moment she appears over there, the her on the side always vanishes. Two of her can never exist. At last he realized, simply do not measure, do not look, and she can remain in the overlap of here and gone, just as we saw in chapter 2. Even so, once he measured, the result was 0. She was fixed to the absent side, but a qubit, apply the H-gate once more, returns to the overlap. This is Metian. Even now, every night he turns off the hallway light. As long as he does not turn around, she is there. A kindness of